Okay, so here is the trick for finding the matrix or the determinant of 3 by 3 matrices only. Okay, so the first thing you need to do is copy the first two columns to the right of the matrix. So 3, 2, 0, 0, 3, 5. So I've rewritten, I haven't rewritten, I've just copied down. So I've got 2 extra columns at the end. Okay, so this is what I'm going to do. So I'm going to multiply the diagonals in the downward direction, and then I'll multiply the diagonals in the upward direction. So let me try to see if I can just do this with red. So the downward products would be this times this times this. So the diagonals this way. So this gives me a -9. Then I'm going to multiply this times this times this. So that gives me a 0. And then I'm going to multiply 4 times 2 times 5. So that gives me a 40. Okay, so that gives me the number 31. Okay, so now I'm going to multiply the diagonals in the upward direction. So 0 times 3 times 4, that gives me 0. So 10 times 3, so that gives me 30. And then this gives me a 0. So all told, the upward directions give me a 30. Okay, so I'm going to add the downward, so 31, and subtract the upward. And the determinant is 1. Kind of nice, huh? All right, let's do that again. So 0, 4, 2, 5, -3, 4. All right, so let's start with going downward. So this gives me 0. This gives me 0. And this gives me 16. So that's 16. And then let's go upward. So this gives me -6. This gives me 0. And this gives me 20. So that gives me 14. Okay, so I'm going to take the downward one, 16, and I'm going to subtract the upwards. So that gives me a determinant of 2. All right, so be careful that this trick only works on 3 by 3 matrices. So this one here, you would want to pick a row or a column to do the determinant of. And I'm going to let you do this on your own and practice it. I got an answer of -6. So I'll just let you go do that because I think it's good to practice on your own without watching me do it again. I don't think you need that. Okay, so here's some properties. Okay, so if I have, it has to be a square matrix. You're noticing here determinants with this cofactor expansion has to be square. So what happens if I do a row operation? Multiply one row of A and add it to another row, right? An elementary row operation to make a new matrix B. If I do that row operation, the determinants are the same. Okay. If 2 rows are interchanged in A to give a new matrix B, then the new matrix B has a determinant that's negative of the determinant of A. So row operations change the determinant. If one row of A is multiplied by K to make a new matrix B, then the new matrix B has a determinant that's K times the determinant of A. Or you can write it like this too. Okay, so sometimes if you have a matrix like this, and if I'm just starting with a 3 by 3, we could do the trick on, right? But let's just kind of practice this row operations because, of course, I'm going to give it to you with letters and you're going to have to figure things out. So let's just see if we can play with this with just a 3 by 3 with numbers. So let's do, well, first I want to identify some new notation. So to say the determinant of this matrix is the same as putting these absolute value bars. So these absolute value bars mean I'm taking the determinant of this matrix. Okay, so from this step to this step, what I did is I multiplied 2 times row 1 and added it to row 2, right? So that I could get a 0 here, right? That's what I want. And 2 times this, oh, look at that, I get 2 zeros. And then between here and here, I added row 1 and row 2. And that gave me a 0 here. So lots of zeros, right? And then did I even, oh no, then I switched these 2 rows, right? These 2 rows, I took the time to switch, so that put the negative out in the front. Now, if I have, oh, I skipped this theorem. This is what I'm using. If I have a triangular matrix, then determinant of A is the product of the entries on the diagonal. So because of cofactor expansion, I get these multiplied together to give me negative 15. This gives me a negative 15, but with this negative on the front, it gives me a 15. Okay, so another important theorem, a square matrix is invertible if and only if the determinant is not 0. So that could be a question. You could be asked, is this matrix invertible? And you would need to find out what the determinant is. So since this does not have a nice row of zeros anywhere, or column of zeros, I'm looking at this and thinking, how about I make this column of zeros. I'd like to make a column of zeros right here. So what I'm going to do is I'm going to multiply negative 4 times row 3 and add it to row 2. And if I do that, this stays the same, and this would stay the same. And so then I would get negative 3, negative 5, 0. So I like that a bunch better. Okay, so now I'm going to expand about this column. So positive, negative, positive, negative, positive, right? So I'd get a positive 1 times the determinant of the matrix left. So this gives me negative 10 plus a 9. So this gives me a determinant of 1. So yes, determinant of A is not 0. I guess it doesn't know yes, it just says if it's invertible. Therefore, A is invertible.